Welcome to the class of high performance computing for scientists and engineers. We are in the fourth module of this course, which is GPU computing. In last few classes, I have given you introduction to GPUs and discussed their utility in high performance computing, and also introduced a programming paradigm for GPUs, which is provided by one of the leading GPU manufacturing vendor NVIDIA, and that is CUDA. In today's class and in the following class also we will continue with that. We will start looking into CUDA programs. We will see how does a CUDA program actually look like, and what are the different components in it, and what are the different hardware and software instances and execution instructions we provide in our CUDA program. So, this class is on introduction to CUDA program. We will discuss few of these issues. CUDA being an API which we usually do not use for our computers, which if they are not supported by CUDA enabled GPUs. For normal computers we do not use CUDA. So, we will see I think it is judicious to have couple of slides on CUDA installation and documentation on CUDA. So, how can we get these softwares, how to install this software, some ideas on that, and then we will see how CUDA programs can be compiled, and then we will look into a sample program which is again provided in the CUDA programming guide as the first CUDA program in that guide, which is addition of two vectors. We will see that how CUDA parallel version of vector addition program does look like, and then we will see some of the components of this program which are typically of importance in order to understand CUDA programming. These are kernels and threads, and how data transfer happens across host and device, and how this device data is managed by the CPU. So, by device we mean GPUs, and by host we mean CPUs in a typical CPU GPU CUDA program. Well, so we are discussing about a CPU GPU program, and this is called a heterogeneous program, or the CPU GPU system when we use it is called a heterogeneous computing, where the serial part of the program or modestly parallel part, that means parallelized in 4 threads, parallelized in 10 threads, that type of part, that part runs in the CPU, and the massively parallel part, which is parallelized in terms of thousands of concurrent instructions, is executed in GPU. So, when usually we talk about a GPU program, it is mostly a heterogeneous paradigm following program, where part of the program is running in CPU, which is sequential or modestly parallel part, and the massively parallel part is running in GPU. Therefore, if we if we look into the program, it looks like that there will be a serial code which is running as an instruction in the host or CPU, and then there will be multiple threads in blocks, and a group of threads will be launched in blocks, and these multiple threads will take care of the parallel component of that program. Again, in the serial part there will be CPU code, again there will be multiple threads which are running in GPU. This we have discussed in detail in last class. Therefore, what we understand from here is that when we try to develop a CUDA program, or when we execute a CUDA program, we have to consider the fact that a part of the program will run in CPU, and at some instance CPU will offload its jobs to the GPU, and the part of the program, that part will run as massively parallelized component of that program in GPUs. Therefore, programming paradigm is required which supports heterogeneous computing, which helps part of the program to run in CPU, and which offshoots the program to GPU, allows communication between CPUs and GPUs, and then executes the program in GPU. So, for that NVIDIA has developed CUDA, which is initially named as Compute Unified Device Architecture. Now they do not use this term, they use the use the name CUDA only for that API, which facilitates GPU executions of programs which are written in common programmer friendly languages like C, Fortran, Python. So, you have a C program or you have a Fortran code, you identify certain part of the program which can be massively parallelized, and now develop a CUDA C or CUDA Fortran program, where over the C or Fortran program you write CUDA instances and ask that parts to be executed in GPUs. This has certain similarity with the previous programming parallelization APIs, like especially with OpenMP, also MPI, which we have understood that we can start with a basic C or Fortran or Python or MATLAB code. We can identify the regions where it can be parallelized and ask the GPUs to take care of that region. Their CUDA instances will be required. So, CUDA is a parallel computing platform as well as programming model, which is developed by NVIDIA. CUDA provides a parallel programming platform, but CUDA itself is a programming model also for general computing using graphics processing units, which we call GPU computing. CUDA helps to develop parallelized programs that scale for large number of cores provided by GPUs, and this is done at the compiler and software support based level, that when you execute a CUDA program, it goes over thousands of threads, maybe 10,000s of threads. Typically, if we think of an OpenMP program running over large number of threads, there will be substantial amount of overhead due to contention, due to memory issues, due to scheduling, due to load balancing, etc. As we increase the number of processors, there will be more overhead. Therefore, if we think of a CUDA program, it is running over large number of processors and there can be huge overhead. However, CUDA itself is designed in such a way that through its own system level support and hardware software based scheduling, it can take care of the overhead, and the overhead is really not that high, and you can get a very high speed up. So, CUDA provides that scalable parallelization over large number of cores present in a GPU. While using CUDA, developers program in popular languages like C, C++, Python, Fortran, etc. And then the parallelism is expressed in form of few basic keywords or few basic CUDA constructs. The serial part of the program runs in CPUs, and the massively parallelized part, which is expressed using the CUDA constructs or CUDA instances, that goes to the GPUs. Now, the entire software, CUDA software, it is available from NVIDIA website as CUDA toolkit, and this CUDA toolkit will run in GPUs. So, if you have NVIDIA GPUs, you can you can download CUDA toolkit from NVIDIA website, and if you have NVIDIA GPUs, you can run it on there. This CUDA toolkit provides a whole set of components required to develop program for GPUs. It contains CUDA drivers and tools need to create, build and run CUDA application, as well as libraries, header files, sample source codes, profilers, debuggers, etc. So, this CUDA toolkit contains everything related to developing the CUDA program, build the executable, compile the CUDA program and run the CUDA program, as well as if you have to debug the program, if you have to profile the program, you will get the supporting files inside the CUDA toolkit. Furthermore, you get documentations inside CUDA toolkit. So, everything related to CUDA toolkit, sample codes, everything related to CUDA is found inside the CUDA toolkit. The only thing you have to do while if you want to write a CUDA program and execute it, you have to download CUDA toolkit from NVIDIA website. The important components are compilers for C, C++, different toolkits, profilers, different tools, profilers, debuggers. The libraries like cuBLAS, cuFFT, cuDance. BLAS is the basic linear algebra library. Many linear algebra solvers, matrix solvers are included in BLAS. So, all the entire BLAS library equipped with CUDA capability is present as cuBLAS library, which is also a part of the NVIDIA CUDA toolkit. There are CUDA samples, there are documentations, and debuggers like CUDA GDBs and their source codes also. So, everything is available inside CUDA toolkit. CUDA toolkit version 11 can be downloaded from NVIDIA website with its relevant release notes. And once we the CUDA toolkit version 11 gives us CUDA software development kit 11.0, it's same, but the version of CUDA is 11.0. However, compute capability we have discussed earlier, it's a hardware support provided for GPU functionalities, and for CUDA 11 it is supported for compute capability 5.2 to 8.0. So, only for the GPUs Maxwell, Pascal, Volta, Turing and Ampere, especially Maxwell to Volta are widely available in market. Turing and Ampere are the newer version, are the most recent versions of GPU. However, all of them are supported by CUDA 11. If gives support for CUDA 11, if you have a GPU which is of a different version, you might not be able to run CUDA 11. So, you have to see what is the compute capability, and there are show you there are standard comments for that, what is the compute capability of the GPU you are using and which version of CUDA is applicable for that. So, once we go to the CUDA toolkit installation guide that is obtained in the NVIDIA site, we can find there are introduction that what CUDA does, and then it gives the system requirement and it tells that which version of you need a CUDA capable GPU. For that you need a supported version of Linux with GCC compiler and toolchain. So, which version of Linux and which version of GCC is required, and then you need NVIDIA CUDA toolkit through which you can install CUDA over that. So, the version, so 3 of the important aspects of installing CUDA will be what is whether you have the right GPU card, whether you have the right operating system, like if you are working in Linux, I have shown you here the Linux installation screenshot, but it can be installed in different platform involving Windows, Mac, etc. So, if you are using a particular operating system, which version of the operating system is supports that CUDA toolkit, and what is the version of GCC that is required for that. You have to check all these things and then you can install CUDA. So, before installation we have to see that the system has a CUDA capable GPU, the system is running a supported version of Linux. You have to see that the compute capability version, that what we mean about the CUDA capable GPU, we have to also see that the compute capability version for that GPU supports the particular version of CUDA you are trying to install. If you are using a older version of GPU, you have to use older version of CUDA also. Well, so verify the system has GCC installed, verify the system has correct kernel headers and development packages, and then download NVIDIA CUDA toolkit and handle conflict installation method. Now, for all this verification whether you have the right version etc., you can find commands inside the CUDA installation guide, that you execute that command and check whether you have the capabilities. After installation, what is mandatory is that you set the environment, the path. If you do not set the right path, you will not get the compiler, you will not find the the compiler will not be executed, as well as executable will not be built. So, you have to set the path in the through bash profile or through module etc. You have to set the right path so that you can find the compiler. Then you have to install persistence writable samples and then verify whether the installation is perfect, and you can optionally you can install debugger. It is a good idea to install debugger while installing CUDA, because when you are writing program, you know that this program is has a massively parallel component. So, part of it is a heterogeneous program with a massively parallel component, part of it will run in CPU, there is data transfer across CPUs and GPUs, and part of it will run in GPU. Therefore, debugging using write commands or debugging using primitive methods may not be very helpful, rather a debugger can give you a more efficient way of identifying the bugs in the code. So, it is very much advisable that you have the debugger installed and use debugger for finding out the errors in the code. Another thing to mention is that when you execute part of the jobs in GPU, you can execute a write statement, you can write something to the screen, but that is supported only for some higher versions of compute capability, or some higher version, some more recent versions of GPU. Older versions of GPU do not support that, and again writing to the, because there are large number of threads, writing to the screen requires certain extra caution, and some practices are to be followed while writing. So instead of giving printf or write star commands and identifying the issues in the code, it's obviously advisable idea, and that is not only for CUDA programming, for any programming, even using C, Fortran basic languages, it is always advisable that you use a debugger and find out the bugs using debugger. All the relevant commands and steps can be found in the installation web page. CUDA compilation is, if you have the when you develop a CUDA file, CUDA C file, the extension is .cu. So, I think I should also write that CUDA C file, its name is name.cu, and CUDA Fortran file will have an extension name.cuf. So, when you build a CUDA file, when you write a CUDA C file, that means a C program in which you write CUDA instances, the file name is to be given as file name.cu. Cu is the extension. So, the compilation command is nvcc vectored.cu is the compilation CUDA file minus o vectored. So, it will build an executable vectored, and then you execute that file, and this will be a heterogeneous program which will run in CPU as well as the part which is CPU asks to GPU to run, that will be executed in the GPUs. NVCC is the compiler, and this executes the binary, dot executes the binary. Now, the question is, CUDA runs in how many threads? Well, writing this, we cannot specify the number of threads, or by environment variable we cannot fix the number of threads. If we remember, in OpenMP we can set and specify the default number of threads, but in CUDA we cannot do that outside the program. Only inside the program, when you use the kernel specification, kernel is the function which will be called by CPU and executed in GPU. We can specify the block number and thread number, and that is the kernel will be executed as a grid of blocks. Each block will have number of threads. So, total number of threads will be NBLK, that is the block number, into NTID, that is the number of threads in which this kernel will be executed. It will be executed in the total number of threads, that is specified by number of blocks and number of threads inside each block as the specifier of the kernel calling, as specified during kernel calling. We cannot control it outside that, or like for MPI you are specifying number of processors in the run command. For OpenMP we are specifying number of threads through the environment variable setup. We cannot do that in CUDA. In CUDA it has to be hard coded inside the program that this is the number of threads we are going to launch. So, if you want to change the number of threads, you have to change these arguments. In how many cores CUDA codes will be executed? Well, in all cores you run threads which are expected to be much more in number compared to the cores. Basically, we will discuss about execution and scheduling of CUDA threads in a later class. So, basically when you launch these threads, group of the threads goes to different streaming multiprocessors, and each streaming multiprocessor runs a large number of threads. Of course, the number of threads are, if not specified otherwise, are usually more than the number of cores. So, they are scheduled within the number of cores. So, they run over all the cores, but there is a scheduling of the threads as well as scheduling of the active cores. Thread execution in cores is scheduled by scheduled at the streaming multiprocessor level scheduler. Programmer cannot specify that. Programmer cannot specify that in this course will be active and this thread will go to this core, like that. In also programmer cannot identify which core is running which of the thread. This is controlled by the SM level scheduler. Now, when you develop a CUDA program for heterogeneous computing, we understand that it runs in both CPU and GPU. There are CUDA optimized libraries like cuBLAS, cuFFT, etc., which completely runs in GPUs. If you yourself develop a program, that will be an integrated CPU plus GPU code, which we are discussing through heterogeneous parallel programming, and part of the program, the purple part will run in the CPU, and the grey part what is shown here, part of that program will go to the GPUs. And then you call the NVIDIA C compiler. It compiles two components of the code. One is the GPU part of the code, which is compiled using an instruction set arguments called PTX, NVIDIA's own assembly language for GPU programs, and that goes to the GPUs. And their CPU part is compiled using the standard C compiler. So, when you are compiling NVCC, GCC compiler is, NVCC means NVIDIA C compiler, which has CUDA for GPU part, and GCC itself is compiling the C part of the code. So, that is running on the CPUs. So, when you run a CUDA program, it is compiled in two components. One component is compiled for GPUs and a binary is built for the GPUs. One component is compiled for the CPUs, and they have an interaction which is done using a wrapper inside the CUDA. So, part of it runs in CPU and part of it goes to the GPU. And if you are using CUDA optimized libraries, they are written in PTX compatible language, and therefore they directly run in the GPUs. But when you write your own program, which is basically a C source code, it has integrated CPU plus GPU code. CPU part is compiled using the standard C compiler, follows the compilation commands syntaxes of standard C compiler and goes to the CPU. The GPU part uses PTX, which is NVIDIA's own assembly compiler for GPUs, and then it goes to the GPUs. And CUDA C programming guide can be found on this particular website, and whatever I am showing in this class and also in some of the subsequent classes will be following CUDA C programming guide only, because it is this guide which specifies how CUDA has to be used. Well, CUDA is also this specifies this is a C programming guide. So, CUDA is also used over other languages like Fortran, Python, etc. And CUDA Fortran compiler is developed jointly by NVIDIA and PGI, and PGI is Portland Group. They have their own compiler sets, and in PGI compiler edition, CUDA Fortran is freely available, which can be the guide can be found here and it can be downloaded from PGI website. So, all of the recent versions of PGI Fortran has CUDA Fortran inside it. Well, now we will look into a CUDA sample CUDA program. We have seen that CUDA program which a developer builds or an application scientist works on is an integrated GPU CPU program, is a heterogeneous program. Part of that runs in CPU, part of that runs in GPU, and we cannot directly ask GPU to run something, we have to always communicate with the CPU. So, we have looked into the process flow in the last class, that is that first you define the variables in the CPU memory, and then CUDA copies the data from CPU to GPU. This is the first step of any CUDA CPU GPU program, that everything is defined in CPU and then CUDA copies the relevant memory from CPU to GPU. Then CPU asks the GPU to launch multiple threads, and while launching these threads, the concurrent instructions stream takes data from the GPU RAM or device RAM and processes the data. So, it writes back the data in the device RAM, and then but the device RAM's data, these files are not again readable by the user. So, it has to be copied back to the CPU, and CPU and GPU is connected via PCI Express bus, and then therefore CUDA instructions are to be given which will copy data from the device RAM or GPU RAM to the CPU RAM. So, these three are the essential instruction stream, essential steps in a CUDA program, that first copy data from CPU to GPU, now give a job to GPU, ask GPUs to execute certain jobs in by launching number of threads. While doing that, they will modify some of the items in the GPU memory and then copy the GPU memory data to the CPU memory data and read the file, write it to the files or read it or do whatever the programmer wants to do. So, now we will see a program which is our first CUDA program, vector addition. There are two vectors of size 100,000, one is vector A, another is vector B, and they are to be added. So, we will run a loop of I is equal to 1 to 100,000 and add each element of the vector. Now, this 100,000 iterations are not done using a CPU C code, rather done as a function which will be executed in 100,000 threads in a GPU. So, how is this done? First is that so there are two parts of the program. First, we inside the C program, first we write the CUDA kernel. This is the part of the program that will be executed in the GPU, and then we write the main function. This is the part which will be executed by the CPU. And this CUDA kernel, which is vec_add, this kernel is called as a function from the GPU in a particular format. We will discuss about this format in the next class. So, what is done here? We first define the number n is equal to 100,000 is the size of the vectors, and then define the vectors. Now, these vectors, what we can, when we specify the values of the vectors, we cannot do anything in the GPU memory. Whatever we will do in the CPU memory. So, these vectors are to be defined in the CPU first. So, we define the vector, the copy of the vector in the CPU. So, what we are trying to find out again, right, is vector C is equal to vector A plus vector B, and that is written as Ci is equal to Ai plus Bi, and this is for I is equal to 1 comma n. For n is equal to 10,000, we are doing Ci is equal to Ai plus Bi. So, this A and B, they are two vectors or two arrays which this addition, whose addition will be done in GPUs, but we cannot define the vectors in GPU, we cannot set their values in the GPU. So, we have to do that in CPU. So, we make a copy of the vector in CPU, which is h underscore A, h underscore B, h stands for the host, CPU is the host, h underscore C, and we make another component which is the device component or GPU component, D underscore A, D underscore B and D underscore C. So, we define h underscore A, h underscore B, h underscore C, which are CPU or host vectors, D underscore A, D underscore B, D underscore C is GPU or device vectors. We cannot do these things in, I mean, even if we are, as we are defining them, we cannot define them inside GPUs. GPU memory we cannot see, we are defining them inside CPUs only. So, one question is that how GPU will know that these vectors exist, we will see that. Now, we define the size of the vectors, which is variable size, which is the floats of n is 10,000, that is the size, that is the number of the elements in the vector. Now, h underscore A, B and C, they have the size of size, and we allocate the CPU vectors using simple malloc. For the vectors which will be the which will rest in the device or GPU, we cannot go inside the GPU and allocate them there. We have to use a CUDA malloc command. This is the command by which CPU allocates spaces in the GPU memory, and the vectors d underscore a, d underscore b and d underscore c, these are the spaces in the GPU memory with this address and the size. They are allocated in the GPU memory by whom? By CPU, and therefore it is not the malloc. CPU is doing this using CUDA. So, this is CUDA malloc. Using the command CUDA malloc, these vectors are allocated in the GPU memory. So, CPU allocate device vectors using CUDA malloc commands. Well, once this is done, in GPU we cannot do anything. We can write the, we have to give the values of the vectors. So, we write the vectors a to be 0.75, all the elements of A is 0.75, all the elements of B is 0.25. We can only initialize them in the host, we cannot do them in GPU. But now this addition will be done in GPU. GPU will do C is equal to A plus B. So, GPU needs to know the values of A and B. Now what we do? We copy the host vectors. Vectors are allocated in the CPU earlier. We copy the vectors, the host vectors to the device vectors. We take the vectors from the CPU, copy them, that is H underscore A is chosen and it is copied to D underscore A in the GPU. Using the command CUDA mem copy, I will discuss about the CUDA mem copy in detail, but it takes the device vector, the host device array, the host array, their size, and writes that this direction of copy will be host to device. So, it will be copied from host to device. H underscore A, all the values of H underscore A for size will be copied to a vector D underscore A, which is now residing in the memory of the device or memory of the GPU. Similarly, H underscore B is copied to D underscore B. So, this copying part is important. Then we define the block size, that there will be 1024 threads in each block. That size of each block is 1024, and the grid size, we have total n number of grid points. So, this is the integer value of n by block size, total number of that. So, in case n is not divisible by 1024, there will be more threads than n. Here n is 100,000, so there is actually more threads than n, but that is okay. But we can see that number of threads are large enough. Of course, number of threads are 100,000. Of course, no GPU has 100,000 cores. So, threads are more than the number of GPU cores. Well, then we call the executable vcat, which will take the grid size, which is number of blocks inside the grid, the block size, number of threads inside each block, and the parameters d underscore a, d underscore b, d underscore c. D underscore a plus d underscore b will be d underscore c, and their size n. And now we call this CUDA kernel. This CUDA kernel is a function which is specified using underscore underscore global underscore underscore specifier, and it returns void. It takes a as d underscore a, b as d underscore b, and c as d underscore c, and size n, and then find out the ID of each thread using, and we will discuss that, finds out the global ID of each thread, which is obtainable based on the grid size and block size, and there is a huge component, important component in CUDA programming called thread algebra, by which we can find out the global ID of the thread based on the local ID of the thread. Local ID means ID of the thread inside the particular block, and global ID means the number of the thread combining all the blocks in the grid. So, you get the global ID of the thread, how we will discuss later. And then if ID is less than n, because we are adding for 10,000, 100,000 numbers, we do this. If ID is greater than that, we do not do that. So, there will be some threads which are not executed, which do not do anything, but up to 100,000 threads, each thread will take one element of C, because these threads have a unique ID starting from 0 to 999999. So, each thread will take one particular element of C A and one particular element of B and add to be C, and therefore they will write to the memory location d_c in the GPU. So this kernel is executed in the GPU, this kernel function, and now GPU variable is not readable to us, so we have to copy it back from device, from the GPU to the host, and the copying direction is device to host. So the which is copied, the source comes later, the destination comes first in CUDA memcopy, and then we just for correctness we see that if the sum is correct, if this the sum is 1 for each element. So if there are 100,000 elements, sum is 100,000, we divide it by n and get 1 as that, and then we have to free the device memory. Is the same way we release the host memory, same way we can use CUDA free to free the device memory. You cannot go into the GPU and free the memory. So this is again executed by CPU and freed. So if we look into the program, these blocks are executed by CPU, and the kernel function is executed by GPU. What is this kernel function? This particular function is the kernel function, which comes with this structure and syntax, and this is executed by the GPU. Allocation, CPU allocates memory in the device via CUDA malloc. Allocation of GPU memories is also done by CPU. CPU copies vectors from host to device. So vectors are initialized at host and then copied from host to device, CPU to GPU using CUDA memcopy. Then we call the kernel, which is a function called by CPU. This function vacadd is a function called by CPU with these arguments, and there is a grid size, block size specifier along with that. It goes to the GPU and it operates. What does it do? It operates on the memory locations of the variables of the arguments passed to the function. It operates at that memory location. Now these memories are the GPU memories. A kernel cannot operate on the CPU memory, it only operates in the GPU memory. A CPU cannot operate in the GPU memory, it can copies, it can allocate GPU memories, it can free GPU memories, it can set the values by copying, but it cannot do any floating point operation using GPU memory or logical operation using GPU memory. The CPU cannot do that, the main program cannot do that, a kernel only can change GPU memories, and that is done by the CUDA kernel. And then the GPU memories are not readable by the CPUs otherwise, so it has to be copied back from CPU to GPU. Well, so we will in the next class we will look into the details of the kernels, what is its specification, what are the syntaxes, etc. Thank you.